At this point, I think we've recapped the basics of integrations. What I would like to do now is basically recap some essential techniques of integration, like for example, integration by parts. Now, let's say integration by parts. This is very important because when we do Fourier series, basically mostly we're going to be involved with this integration by parts. Where does this start? You first of all need to remember that if you were to differentiate a product of two functions, let's say we've got two functions u and a v with respect to x, this would come up as a derivative of u with respect to x, derivative of u, sorry, with respect to x multiplied by v plus the derivative of v with respect to x multiplied by u. Here I'm just saying x to mean the independent variable. It could be t, could be another independent variable depending on the situation. Or we can just now abbreviate this thing, say u prime multiplied by v plus v prime multiplied by u. And this basically was the product rule of product rule for differentiation. This was product rule. So now, having understood in the previous situation that differentiation is the inverse of integration. So now, if I introduce an inverse here to dx of u times v, I'm just going to write it roughly. Then if I introduce it on both sides, I'll basically have this side u prime times v plus v prime by u. Now notice here that we put integration and differentiation as inverse processes. It looks basically like we're in a situation where we've got e to the power ln of x, same thing which could be ln of e to the power of x, and that would give us x. Now we get back to the variable which is being acted upon. In this case, what is being acted upon is uv here, which means if this is e and this is ln, we'll get uv. If this is e and this is ln, we'll get uv. So uv, u times v, will be equal to this integral. In this case, we can say this integral is integral of u prime times v plus integral of v prime times u. In the final analysis, this formula gives us roughly our formula for integration by parts. In this case, they say we're given, we could make this part subject to the formula. It doesn't really matter how they make this one subject to the formula to give us an idea how to integrate by parts. So let's say we've got v prime here and the u with respect to x. Let's say we're integrating to x, that will be equals to u v minus the integral of u prime v dx. Now, if you look at this, what we've got here is almost similar to what we've got there. So if we look at it without analyzing very careful, we might think that we're going to move in circles here, because this can also be made subject to formula. But anyway, this can be understood quickly with an example. Let's say we've got now integral of x e to the power 2x dx. So according to this formula, I have to declare one of my functions under integral sign as a function which has already been differentiated, and another function as a u which is not been differentiated. Now if I cross the equal sign, I think you can see that now I still need my u which is there, and I need a v, but a v can only come from its derivative by process of integration. and then here I need u prime, but u prime can only come from u by process of differentiation. So now I've got to choose these functions in a careful way that I'll basically be able to conclude this integration. My recommendation here is that you must know that these two functions have got a certain different nature in terms of differentiation. Notice that e to the power 2x, you can differentiate it infinite times without really getting to a constant of 0. But x, you can differentiate it a finite number of times, then basically the derivative should be 0. So what I recommend that the function which can be differentiated infinite times without getting to 0, make it your v prime. So in this case, we're going to say our u is equals to our x, and our v prime is equals to e to the power of 2x. Then basically, according to the formula here, we need u prime, then we move from here to u prime, which is going to be equals to 1. And then this is v prime. The integration, we said it will be limited integral. Integral of a exponential function is an exponential function, so it's equal to e to the power of 2x, but divided by the derivative of the argument. Now once you've done that way, according to the formula, you can see that this says bring together v and u. So bring together v and u, then take v prime and v under integral sign. So take v prime and v under integral sign, and then what you do is you subtract that. You subtract this was integral sign. So in this case now, this is going to come up as x e to the power 2x over 2 minus integral of 1 times e to the power 2x over 2 dx. You can see that 1 over 2 is a constant. You can take it outside the integral sign. Then we give x e to the power of 2x all over 2 minus half e to the power of 2x dx. Now when we are here now, we can actually apply what we did there, because we integrated this to get to there. Then this final answer here will give us x e to the power 2x over 2 minus the integral of this is basically that, so it's going to be e 2x multiplied by half, which will give us 4 plus c. So that integral there will be now complete. I hope you basically follow this integration very well. I'll give you another next example just to try to consolidate this. Now let's look at the next example on integration by parts. Let's say we've got integral of x squared cosine nx dx. Notice that n is a constant. Now again, if you look at these two functions, cosine can be differentiated infinite number of times without circling at 0, but x squared can be differentiated at least, let's say, up to maybe 2 times. Third time, fourth, and also on, they will be equal to 0. So our choice must be u is equals to x squared, and then u prime would be equals to 2x, and our v prime is going to be equal to cos n x, and our v, which is the integral of that, is going to be sine n x divided by the derivative argument, which is n. Then again, v in the formula, v and u come together, and there is 2 under integral sign, and we subtract them. then this integral is going to be equals to x squared sine nx all over n minus the integral. Let's immediately take out 2 over n outside the integral sign and say x sine nx dx. So which means now here we basically at the initial situation, but the power of x now is 1. So we can repeat the integration by parts. Now our choice of u will still going to be x, and the u prime in this case is going to be 1, and our v prime is going to be sine nx. Then our v in this case sine is a derivative. Could say that sine is a derivative of minus cosine nx divided by the derivative argument. Let's cancel that and put an equal sign there. Then we can now copy this as x squared sine nx over n minus 2 over n. Let's have a big bracket, a square bracket. Now we've got this and that, and the integral sign is going to give us minus x cosine nx all over n, and then these 2 will go on the integral sign with a minus, and then this is going to be minus and minus will make us a plus. Then you've got integral of cosine nx dx, and you can have a 1 over n outside the integral sign, then you stop there. So you see now after differentiating x squared twice, we're at 1, so the next derivative will be 0, but at least now this here we've got a single function to integrate. You can integrate simply. Then our final integral here will look like x squared sine nx over n. Now removing the brackets here, minus and minus will give us a plus. Then we got 2x cosine nx all over n squared. Then the integral of cos is sine, because cos n is a derivative. So but if you divide it by the derivative of the argument, which will give us n squared, and this n here will give us n cubed. So we're going to have this plus, so minus, because there's a minus sign outside there. Let's have this as minus sine nx all over n cubed plus c. You can double check that integral whether it's done correctly, but this was supposed to do. So basically what I'm trying to highlight here is that when you've got higher powers of x, basically you can repeat this integration. In this case it was 2. We repeated integration by parts twice. Then immediately after twice differentiating, you get to a standard integral, which you can integrate immediately and come to the end of the problem. I hope that helps you to revise integration. So try to do the following also. Let's say we've got x to the power 3 e to the power of x dx, and integral of let's say sine 3x multiplied by a to the power of x. Try to do this one, but this one here is going to present new problems, which I'm going to explain in the last example I'm going to give you later. Thank you. Let's stop there for a while. The last exercise I gave you in the previous session was of this nature. You had something like let's say e to the power of x and cosine let's say 2x dx. Still on integration by parts. If you remember what I said about the choice of your u and v prime, in this case here we've got a different situation, because cosine can be integrated infinite number of times without getting to derivative being 0, and the e has got a similar characteristics. So in this case here, what is important when you choose your u and v, you can choose any, but in your repeated process of integrating by parts, you must make sure that you are consistent in choosing your v's. What I mean basically, if I initially choose my u, in this case to be e of x, my u prime is going to be e of x, and my v prime in this case is going to be cosine of 2x. My v is going to be sine of 2x divided by the derivative argument. In this case, if I'm going to repeat this integration by parts, which I'm going to do, I still have got to take my u to be the exponential function and my v prime to be the trigonometric function. Then that way I'll be able to conclude the integration easily. So in this kind of integration, let's call this integral I. Then if we start our process of integration, which we've already started here, we then multiply our u and v, take this under integral sign with the subtractions before the integral sign. So which means that this integral is going to be e to the power of x sine of 2x over 2 minus the integral of e x sine of 2x. Let's put this to outside integral sign. Now when you look at this, it looks like we're basically at the initial point there, and it could seem as if this process is never going to end, but this process will end as long as we work with our eyes opened and monitoring what is happening closely. Now in our repetition of integration by parts, basically what's going to happen, we can still say our u is equals to e of x, and our u prime is going to be e of x. Our v prime is going to be sine of 2x, and our v is going to be equals to minus cosine of 2x all over 2. So if you do the same pattern, these two and those two on the integral sign, a minus sign before, what is going to happen now, we're going to have our integral continuity being e to the power of x sine 2x all over 2, and then minus half in brackets. We're going to have what we have here. This is that times that, which is e x cosine 2x over 2 with a minus sign before. Now these two multiplied and minus sign there, it gives us a plus integral of e to the power x cosine 2x dx, and our half outside integral sign. Then if we look at this carefully, you will see that this integral is the one which you started with, which in this case it is I. And once we see that appearing, that's why I said you must monitor carefully what's happening so that you can be able to stop. Once you see that happening, you stop repeating your integration by parts. Usually in this kind of case, you will do integration by parts twice, and then the integration you started must reappear. Now how do you conclude this? Let's first of all remove these big square brackets, which means we're going to have e to the power of x sine 2x over 2. Minus sign will give us a plus, then you get e to the power of x cosine 2x all over 4. Then this minus sign, that plus sign, is going to give us a minus, and then we're going to have a minus 1/4 multiplying I, because that is our I there. So now at this stage now we've got I on the right hand side of the equation and the I on the left hand side. So we can group these i's together, which is going to give us I plus 1/4 of I equals to e to the power of x sine 2x all over 2 plus e to the power x cosine 2x all over 4. Now our target at the beginning here was to get I, and now we've got I in the equation here. So what we can do, we can take a common factor I and basically have inside the 1 plus 1/4 equals to e to the power of x sine 2x all over 2 plus e to the power x cos 2x all over 4. Then this is basically 1/4 plus 4/4, which is 5/4. So we got 5 over 4 times I equals to e power x sine 2x all over 2 plus e to the power x cosine 2x all over 4. Now we can make our I substitute the formula. Remember, I is equals to our integral, which is e to the power of x cosine 2x dx, and then if we make it substitute the formula here, we'll have to divide both sides by 5 over 4, which will give us something like 4 over 5, because we've got to invert that fraction, multiplied by e to the power of x sine 2x all over 2 plus e to the power of x cosine 2x all over 4 plus a c. Then what is left now is just to simplify this integral, which we can simplify as follows. This 2 and that 4 will simplify, got 2 over, so we get 2 ex sine 2x all over 5, and then this side we're going to have e to the power x cosine 2x all over 5 plus c. I hope this is just double check that is correct. This 2 here simplifies this 2 there, get a 2, and then you've got a 5 here. Now here we get here 4 simplifies with that 4, you get a 5 there. Then that will be your answer to your integral. I hope this technique is recapped, and you must be able to do this kind of integration by parts very easy without any problem. Now, what we must also remember as part of techniques of integration is integration using partial fractions. In this case, we'll be looking at exercise of this nature. Let's say integrating x dx over x plus 1 multiplied by x plus 2. This type of integration, basically, we would need the technique of partial fractions, whereby we would basically simplify, break down this fraction into smaller fractions, which could possibly integrate, maybe using a linear form of integral or power rule, depending what it simplifies to. So that basically motivates us to break a bit and revise how do we break a fraction, an algebraic fraction like x over x plus 1 by x plus 2 into partial fractions, in this case into two fractions with denominators x plus 1 and x plus 2. That I'm going to present in another section separately, focused on partial fractions. But for now, I think you can carry on revising and revising your integrals and practicing integration basically. But most important, one mustn't lose sight of the basic standard forms of integrals. Like for example, let's say one, most essential, the power rule, whereby we were integrating a function of this nature. Derivative of the argument is always there, because here the function is the power function. Then this, we know that we should always remember that it integrates to f to the power n1 plus c, where n is different from -1. And the 2, the logarithmic, this is power form, the power rule form. Then the logarithmic form, when n is -1, f prime of x over f of x dx, that will be ln of f of x plus c. And then you get 3 exponential form of integrals, e to the power of f of x multiplied by f of x prime dx. You know that this is equals to e to the power f of x plus c. You must understand how this comes to that. Then thirdly, we'll basically come to trig functions. For example, if we sine, you've got f of x prime sine, let's say cosine f of x dx. So you must know that here you will always call upon the immediate derivative of the function, which is acting on f of x, and here is a f of x prime. So that will be sine f of x plus c. So you call upon the immediate derivative of the function, then you get that. So you must notice that when you differentiate this side, it will basically the derivative of sine, which is cos, multiplied by the derivative of the argument, which gives us that. And all the trigonometric functions basically are going to be worked out in a similar fashion. Otherwise, these are the basics involving general forms of the functions, in this case a chain rule. You must be able to remember this and use it accurately in solving your problem, because without this remembering integration, you might find that some part of your course are going to be a bit impossible. I'm going to stop there and encourage you to revise further and make sure that you know integration and differentiation and move smoothly in your course. Thank you. At this stage, I would like to recap important facts about integration. Straight integration. I hope you still remember that integration is closely related to differentiation. Actually, in simple, I could say integration and differentiation are two sides of the same coin. And if you cannot differentiate properly, it would be very difficult to integrate properly. Actually, integration should be understood as inverse processes. Now, as I can use this arrow to basically say I can move from differentiation, from integration to differentiation, and vice versa. So now, let's say we're given a function like y is equals to sine x, and could be sine, also could be sine x plus 2, and maybe let's say also sine x plus 3, or generally let's say we're given sine x plus a constant So I hope you notice that the first instance here, the constant is 0. Now, you should understand that by process of differentiation, if I differentiate this y with respect to x, the answer here basically will be cosine x. What I'm trying to do here, I'm trying to understand how integration relates to differentiation. So now you see that cosine x is the derivative of all this family of functions. So normally when you start integration, remember we start with the indefinite integrals, and in this case, if we now want to move from a derivative back to an integral, which is the function which was differentiated, basically would use the sign. Integral sign is integral of cosine x and dx. So in this case, basically we should understand the sign as an integral sign. At the same time, we can take it as a kind of a question which is asking us that here is a derivative with respect to x, which function was differentiated. In this case, if we look at this column functions here, you cannot precisely say whether it was cosine x, whether it was sine x plus 2, or sine x plus 3, or sine x plus any constant c. So in that case, if we were to answer this thing just from this, we would say the function was differentiated to get this derivative, and the integral sign is equals to sine x plus c. And that c here is a real number standing for the range of possible constants throughout this column of functions. So in other words, what I'm trying to say here is that whenever you're given a derivative, in this case cos, to recover what the function was differentiated, we must integrate. As you can see here, we started by differentiating a function, we go to a derivative. Now from differentiation back to the function, we are integrating. So if you understand this properly, it will be very good. Then what it follows is basically to know all the standard derivatives, so that the standard derivatives and the way that the functions are differentiated get those derivatives, then basically you probably have got answers for all your standard integrals. But the story does not end there. What actually message I put across here is that under the integral sign, what must sit under the integral sign must be a derivative but it's not true that things are also going to be given in such an easy way that you can clearly see what is your answer for integral. For example, let's say if I had a function like let's say cos 2x dx. Now if I were to find the function which was differentiated to get this kind of a function, I must first of all think of the fact that this is supposed to be a derivative. But if this is a derivative, remember we said that a derivative function is always the derivative of the immediate function multiplied by the derivative of the argument. But in this case here, the function does not change the argument if it's being differentiated. In this case, the argument is 2x. So if we know that the derivative of the cosine is the derivative of sine. So now if we are being asked what is the function which is differentiated to get cosine of 2x, we cannot answer the question unless and until we've transformed this into a complete derivative. And the complete derivative is the immediate derivative of the function multiplied by the derivative of argument. So there's something which is lacking here. So what I want to do in the next line, we should try to transform this to a derivative, and normally that's easy doing it this way. let's say now, we know that the derivative of this argument will be 2. So we are basically looking at 2 under this integral, then cos 2x dx. But once we've done that, this equal sign here is no longer balancing because these two sides are not equal. So in order to balance that, we normally put a 1, which is a 2 over 2, to take advantage of that 2 as a derivative of the argument. And then we basically factor out what is redundant in the integral here, which in this case is half. Then have an integral 2 cos 2x dx. Now, if we look at this other than the integral sign now, there is a complete derivative there. There is cos as a immediate derivative of sine, and there is 2 here as the derivative of the argument. Now we can answer the question that what is under integral there is a derivative of sine 2x. In this case, we write half times the function which was differentiated to get us under the integral sign, which is sine 2x, and then we can add a c, and then simplify, write this thing as sine 2x over 2 plus c. Right at this stage here, we can actually have another kind of a summary. If we look at what has happened here in relation to our initial integral, we'll say the integral of a function is basically the immediate integral of the function. Now the immediate function where this cos is coming from, which is sine, then divided by the derivative of the argument. And this, if you listen carefully to what I had said before, we had said the derivative of a function is the immediate derivative of a function multiplied by the derivative of the argument. But now, from here to there, I could say also the integral of a function is the immediate integral of a function, which is sine, divided by the derivative of the argument, which actually goes back to emphasize the fact that the differentiation is the inverse process of integration, or integration is the inverse process of differentiation. Now, let's explore this further with some other functions. Like, let's say, let's think of first, you can think of a function like the exponential function. What we know about the exponential function, we know that, let's say, start with a natural base e to the power of x. We know that the derivative is equals to e to the power of x multiplied by ln of the base multiplied by the derivative of the argument. And taking it in generally, then we'll say y equals to e to the power of f of x. The derivative would be e to the power of f of x ln of the base multiplied by f prime. Using a general base, which is not natural, we say a to the power of f of x, and the derivative, so this is derivative, the derivative will be a to the power of f of x multiplied by ln of a multiplied by the derivative of the argument. Now, as I've said, I said now if we integrate a function like say e to the power of 2x dx, which is very similar to what we've done with sine and cosine before. You see, in this case here, we would basically say what is under integral sign here is not the usual, is the not complete usual derivative of the exponential sign, because we are looking basically the derivative of the argument. So we would basically do this a similar transformation by taking the integral and say e to the power of 2x respect to x and doing some transformation there. We can now insert a 2 here over a 2 in a similar way we did to the sign. In the next stage, Pascal factor out half and have have integral of 2e to the power 2x dx. Then once this expression under integral sign is adopted, the form of the derivative of the function, remember ln of e is 1, so the 1 is included there as a factor, and then f prime is included as 2. Then we can now answer the question that the derivative of this function is equals to e to the power 2x, but multiplied by this constant which is outside the integral sign plus a c. Then simplifying, we've got e to the power of 2x over 2 plus c. Then again I can repeat exactly the same thing, that from this initial step here to that final step there, the integral of this function is actually the immediate integral, which is e to the power 2x, but it must be divided by the derivative argument, then add c. That's how we are going to integrate this kind of functions. It's very important to know how to integrate exponential functions, because when we get to complex Fourier series, we'll be basically constantly integrating the exponential functions. Now let's take another general example. Let's say we've got the integral of 5 to the power x squared multiplied by x dx. Now if you analyze properly there, this case is that we're talking about the derivative of this nature. So partly I think you can see that the derivative of the argument here is 2x, and we've got 2 here, but we've got x here but don't have a 2, and also this derivative normally is multiplied by ln of the base, and that we don't have. So when we're going to integrate this, we've got to take all that into consideration in order to transform what is under integral sign here to be a derivative. So we're going to write integral. We get our 2x there over 2, and we can also have our ln 5 there over ln 5 multiplied by 5x squared dx. I hope you see that there's nothing wrong with what you've done here. The quantity sign holds because this is a 2 over 2 is a 1. This is a ln of 5 over ln of 5, which is also a 1. So we've transformed the integral, but in an equivalent way, so to speak. So we will now factor out all what is redundant and integral sign, which will basically be 1 over 2 ln 5, and then the integral sign will be remain with 2x, which is derivative argument, ln 5, which is ln of the base, and by 5 to the power x squared dx. Then immediately we can now see that this structure here is exactly the same structure we've got there. Then we can ask ourselves, where does this come from as a derivative? And you can see clearly it comes up from something like this. In this case, now we just in the integral we're going to identify our base, identify our f of x. Then here we would say this integral is equals to 5x squared multiplied by 1 over 2 ln 5 plus c. And then basically what's going to happen now is that we can now simplify this and write 5x squared over 2 ln of 5 plus c. That way I think I've just shortly revised with you the important integrals, exponential functions, and the trigonometric functions. And what is important basically is to understand the relationship of integral and derivative